So thanks. So welcome everybody to the class. As always, you can type your name into the chat so that we have a record of your attendance so that we can make sure to get you your data for next week. It seemed like the data distribution went really well this week. Everybody got their data on time, so that's good to hear. And yes, I'm sorry about last week. We had a snowstorm, and when we have a snowstorm, the kids are not at school, and it's not easy for me to do very many things. So I'm sorry about canceling last week, but we'll have a makeup session for that. The original plan was to finish on May 22nd, and instead we'll have one extra class, so we'll finish on May 29th instead of on May 22nd. So that we can get through everything. Okay, so I hope everybody's doing fine. The just want to let you know that I don't know to what extent. Oh, this. I need to change the settings. Sorry, it keeps kicking me off. Um, sorry. Share screen. Keeps kicking me off anytime I let it sleep for too long. So I don't know how many people are following world politics, but there have been, this is a government supported program, and there have been some potential problems with government supported programs in the US dealing with foreign countries, but I can guarantee that at the very least for this semester we're going to be fine. So the program will finish for this year. We're awaiting guidance for what's going to happen in the future, but there is no risk of the program getting shut down this year. So I just wanted to make sure everybody knows that. Here in the U.S., there's been a lot of upheaval and a lot of changes in terms of how government is funding things. So, but we are okay for the rest of this year, um, whether it's from the NSF or whether it's not. Okay. So I just wanted to let you know that. Okay, good. So I hope everybody's doing fine. I know it's been 2 weeks, so instead of jumping right into the homework exercises, I want to take a little bit of time to review what we did 2 weeks ago, and then we can go over the homework exercises, and we're going to do a couple of new things today. We're going to talk a little bit more about the relationship between derivatives and graphing. And then we're also going to talk about the chain rule, which is our last major rule for how to take derivatives, right? We've done the product rule and the quotient rule and the power rule, and we talked about how to take the derivatives of trigonometric functions also. So the last major rule, and in some ways one of the most important, is the chain rule, and we're going to talk about that today. Okay? But before we start with that, why don't we just review what we've talked about in terms of what derivatives mean? What do derivatives have to do with what a function looks like? So this is a result we had from before. This is called the first derivative test. Okay, and so suppose we have a continuous function that has a critical number c, then we have these kind of three cases, which are written here in these bullet points, but I'm going to draw them in three different boxes because usually these things are easier to understand when you visualize them. So I'm going to draw three different sets of axes here in my three boxes. So the first one says if f prime of x changes from positive to negative at c, then f has a local maximum at c. So in all of these, I'll label the point c along the x-axis over here. It's going to be the same point on all of the graph. And remember what f prime means. It means the slope of the tangent line. And that means that if f prime of x is positive, if the derivative is positive, that means the function is increasing. And if the derivative is negative, the function is decreasing. So if you change from positive to negative, it means that the function goes from increasing to decreasing. And at that moment where it changes, right up here, what the first derivative test tells you is that you have a local maximum at C because it starts off increasing over here on this part of the graph, and then it hits the top, and then it starts decreasing on this part of the graph. So we go from increasing to decreasing. That's a local maximum. Okay, so the second bullet point is the opposite of the first bullet point, right? So it says if you go from negative to positive, the derivative goes from negative to positive, which means the function goes from decreasing to increasing. That means that f has a local minimum at c. So the way the picture looks here would be something like this. We go from negative to positive, and at that point where it changes, this critical number c, here we have, this is the local minimum. Okay. By the way, remember critical number c, the definition, this means either f prime of c equals 0 or f prime of c does not exist. Okay, both of those are referred to a critical point. And then lastly, if f prime of x does not change sign at c, so you can have a critical number where f prime of x doesn't change sign. And an example of that would be the graph of y equals x cubed. You have something that kind of looks like this. This is in fact an actual function. We can say this is the graph. Oh, maybe let me sorry, let me undo that. I want something where this is going to happen at c. So if I have a graph maybe like this, so for instance, this could be y equals x minus c cubed. We'll see that this is a reasonable choice for what the equation of this graph is going to be. Well, we have a critical point here because the tangent line has slope 0, right? The derivative is 0 here because the tangent line has slope 0. It's a horizontal tangent line, but f prime of x doesn't change sign. As we move, as x is increasing, what's happening to f? Well, it starts here, it's increasing, 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 and then it flattens out, and then it starts increasing again, which means that the derivative here is positive, 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 and then it flattens out briefly, it goes to 0, and then it gets positive again, which means it doesn't change sign. It never becomes negative. It starts positive and it finishes positive. But at one point, it goes down to 0 and then goes back up to being positive. So when that happens, this critical point is not a local minimum or a local maximum. And you can see that from looking at the graph here, right? This point C, you don't have a local minimum or a local maximum, right? It's not bigger than everything around it, because if you go to the right, it can get even bigger. And it's not smaller than everything around it, because if you go to the left, it will get smaller. So this point C here is not local max or local min. Okay, and so this is the first derivative test. If you have a critical number and you want to know whether you have a local maximum, a local minimum, or neither, you can check to see how the sign of the derivative changes around that point. Going from positive to negative is a local max, negative to positive is a local min, and if it stays the same, it's neither a local minimum nor a local maximum. Okay, and I guess I should say that this is all, if you want to follow along with the textbook, this is all section 3.3 in the book. Okay.
Yeah,
Yes,
yes, sir.
question? Question, yes,
Yep.
Prince.
Yeah, is a horizontal line become a tangent line where the zero meet at the point of C?
Yeah. So the tangent
Okay,
line is exactly horizontal here, which is a little
okay,
bit weird to look at, to think about it. But if you see, because this graph gets so flat here, it turns out that the line that is just kind of touching the graph at the same slope is exactly the horizontal line, even though it cuts the graph through.
yeah, okay, yeah. You said that it's false. Yeah, you said that the derivative falls on zero, and zero on a point on a line, which is the horizontal and the vertical, it has to be at the center. Why is it that the derivative comes 9 and 4 at the point of C?
Right. So what I mean here is
Bueno,
that f prime of
es un
c is
question.
equal to 0, right? This is when I say I have
Sí,
here f
fueron
prime
para
of
una
c
alguna
is equal to, sorry, let me
figura.
just mute everybody. So f prime of c is equal to 0. That means that at the point C, the tangent line has a slope of 0. and a slope of 0 means horizontal. So this C is a critical number, but despite the fact that it's a critical number, it's not a local minimum and it's not a local maximum. It's actually what's called an inflection point. It's this strange value here, but the tangent line is still horizontal, and you still have this critical number at C, but it's not a local minimum or a local maximum. So I'm not sure if I
Okay,
answered your
okay.
question. Is that helpful, or do you want to ask again?
Yeah, yeah. So yeah, thank you. So because our f prime or c equal to zero, that
Yeah,
is why make the tangent line to ascend from the c, which is the point of c, to be equal to zero. Because any number,
exactly.
if I may get it clearly, any number that comes after the point of c is what relating to zero.
hmm Yeah, so right,
Oh,
when we plug in C to the derivative, that's the specific place where the tangent line is 0. Right. If I took a point after C, these tangent lines would have positive slope. And if I take a point before C, the tangent lines also have positive slope. But it's only at C the tangent line will have 0 slope.
okay.
And so
So that
that's
is what make it to be not. That is what make it not to be local maximum or local minimum.
right, exactly, because the tangent lines have positive slope before C and after C. Over
Thank
here,
you.
you
Thank you.
switch from positive to negative, but here it's just positive and then stays positive. So that's why it's
Okay.
not a local maximum or minimum.
Okay.
That all,
Thank you.
boss?
Okay, does that make sense? Yes, question?
Yeah, that all, boss.
Yes, James.
Yeah, looking at the graph, y is equal to s cube is kind of a cubic function. Can a
hmm
cubic function have a local maximum and local minimum?
Yeah, it can. So, I mean, we'll actually see an example of this. So we'll do that today. Yeah, we'll see an
Yeah.
example of that today where it doesn't look like this and it actually does have a local minimum and a local maximum.
So can I ask about the graph in the middle?
Sure.
They want the parabola open upward.
hmm
It's saying it changes from negative to positive at
Yeah.
constraint of c.
hmm
So how does that graph goes? Where do the graph starts from? Because we say it
Oh, I
starts
mean, we
from
can.
negative.
Yeah. So I'm just drawing the important part of the graph. Away from C, anything can happen, right? So I just didn't draw that part of the graph, but I mean, the graph could be anything away from C. All that matters that I'm focusing on is this point C over here. So you can do whatever you want for this graph away from C. But the point is, near C, it goes from negative slope tangent line to positive slope tangent line, and that change happens at C. So in terms of being a
Thank you.
local minimum, it doesn't care about what happens in the rest of the graph. It's just what's going on near C.
Thank you, Dalabas.
You're welcome. Other questions? Okay. Okay. So this is this test that we saw before. It helps you figure out what maxima and minima look like. So another thing that I want to review is we talked about what the second derivative means. This is what's called concavity. So the second derivative, remember where we use two primes of f, is the function we get when we take the derivative of f twice. And we saw before that if f double prime of x is greater than 0 on an interval, then the graph of x is called concave up on that interval. And if f double prime of x is less than 0 on an interval, then the graph of f of x is concave down on that interval. So let me just draw again what this looks like. So what does concave up look like? That looks like something like this, like an upward pointing parabola. And concave down looks like a downward pointing parabola, something like this, right? And then there's also segments, right? Concave down, it doesn't have to be a whole parabola. You can have a segment like this. This is also concave down. Maybe you have some function that's only defined on this interval and on this interval, and it's not defined in between. And likewise, concave up things look like this. And you should generally think of concave up as holds water, right? Or it's something that water can be on top of and holds water. And for concave down, you should think of it as like spills water. Okay, so water that's underneath here is just going to fall. It's not going to be held up by anything. Okay. So this is the difference between concave up and concave down, and these features of a graph can be recognized by computing the second derivative. Okay, so just like the first derivative, when it's positive, the graph is increasing, and when it's negative, the graph is decreasing. For the second derivative, when it's positive, the graph is concave up, and when it's negative, the graph is concave down. Okay, so this is the geometric and visual meaning of the second derivative. Okay, and so again, maybe just a quick example of this, just a very basic example is if you have y equals x squared, or f of x equals x squared, then you have f prime of x, one derivative is 2x, and f double prime of x, that's two derivatives, and that's just 2, right? Because it's 2x to the 1, right? It's 2x to the 1. You bring the 1 down, that just becomes 2 times x to the 0. Maybe I can say that's 2 times 1 times x to the 0, which is just the same as 2. And this 2 is positive. So this is going to tell us that it's concave up. And we see when we draw the parabola that it is concave up. This is y equals x squared. This is the most familiar parabola. And it is certainly concave up when you draw the graph. Okay. So the concave up comes from the fact that the second derivative here is positive. And the more positive it is, the more concave it is, the more quickly it curls. And if it's just positive, but just a little positive, it's going to be less concave. Like it'll still be concave up, but it's going to look a little more like a straight line. It's not going to curve as much. This is the meaning of the second derivative there. Okay, questions?
That overs?
Yes, James.
Yeah, like you said, it depends on the second derivative. If it's less than 0 or greater than 0, determine it will be concave up or concave down.
Mm-hmm.
So looking at the graph, are we going to look at the parabola opening up or the graph opening up and down to determine to be concave up or concave down?
Yeah, I mean, so there's two things, right? You can look at the graph itself and determine it, or you can do it computationally. So what you usually will have is you'll have a function, and the function will have certain ranges where it's concave up and other ranges where it's concave down. The graph won't necessarily be all concave up or all concave down, but it'll have different parts that have different properties. And that's what's going to happen if the second derivative is actually some function. But in this example, the second derivative is just a constant. It's just 2. And so that means it's greater than 0 everywhere because this doesn't depend on x. So in this case, for drawing the parabola, it's just going to be concave up everywhere. Okay, but other functions that we'll see will have areas where they're concave up and other areas where they're concave down. And knowing that will help you graph the function. Okay. Other questions?
Yeah, there.
Yes, Prince.
Yeah, I have a concern to y is equal to s squared,
Mm-hmm.
and then getting the answer of the prime f of prime to be
Mhm.
2. So
Well, yeah. Mm-hmm.
taking the derivative, how can this 2 as a power become the coefficient here?
Well, so the first derivative, remember, this is the power rule, right? When you take a derivative, the exponent goes down and becomes the coefficient, and then the exponent itself gets decreased by 1, right? So
Oh, okay, okay.
remember, this
Well
is this is
understood.
how the
Okay.
power rule works, right? This is how we take the derivative of a polynomial.
It's
So
okay.
okay,
Understood.
good, good. Yeah. All right, other questions? Okay, so this is the meaning of the second derivative. And one more definition that I want to just recall here is the definition of inflection point. Okay, so remember that a point is called an inflection point if f of x is continuous at that point and the graph goes from being concave down to concave up, or from concave up to concave down at that point. So remember, we talked about local minima and local maximum is like that was when the function goes from increasing to decreasing. So that's when the first derivative goes from being positive to being negative, or from being negative to being positive. Inflection point is the same idea, but for the second derivative. It goes from being concave down to concave up, or from concave up to concave down at that point. And what I should notice is that if the second derivative exists at an inflection point, then it's got to be equal to zero there, right? Because remember, f double prime of c greater than zero means concave up, and f double prime of c less than zero means concave down. And so if at your point C, you go from being concave up to concave down, that means your second derivative is going from being positive to being negative. So when you make that transition, it's got to be zero. That's how you go from positive to negative. You have to pass through zero, as long as the second derivative actually exists there. So the example, the classic example of an inflection point, is this y equals x cubed that we drew before. So if you draw the graph of y equals x cubed, it looks like this. Okay, this is the graph of y equals x cubed. And let's look at c equals 0, right? So we have, well, if f of x is equal to x cubed, then f prime of x, using the power rule, remember we bring the 3 down, so that becomes 3x, and then the exponent goes down by 1, so 3x squared. F double prime of x is what? Now we bring the 2 down, and it gets multiplied by the 3. So 2 times 3 is 6, and then the exponent also goes down by 1. So instead of 3x squared, you get 6x. And let's notice, so this is the second derivative. F double prime of x is equal to 6x. And so we see that if x is less than 0, then f double prime of x equals 6x is also less than 0. And if x is greater than 0, then f double prime of x, which is 6x, is going to be greater than 0. And so what this shows is that if x is less than 0, the second derivative is less than 0. If x is greater than 0, the second derivative is greater than 0. And so that means it makes a transition. When x is equal to 0, the second derivative is equal to 0, and the graph goes from being concave down to concave up. So this tells us that x equals 0 is an inflection point. Right, x equals 0 is an inflection point because the graph goes from being concave down, negative second derivative, to being concave up, positive second derivative. And we see that here on the graph, right? We see we have this part of the graph over here, which is concave down, right? You can see that algebraically because 6x is the second derivative. That's less than 0 when x is negative. But you can also just see it graphically. This looks like it's concave down. It spills water. And then the other part of the graph, on the positive part of the x-axis, this part is concave up, right? And again, we can see this algebraically. The second derivative is positive when x is positive, so that means it's concave up. Or you can just look at the graph. This is concave up. It's curving up. It's holding water. And so at that point in between, at the transition point there between concave down and concave up, you have the inflection point, which is right here at c equals 0. So this is the inflection point. Okay. So y equals x cubed is the most basic example of an inflection point, and it really illustrates the concept. You go from concave down to concave up, and at that point where it changes, you're going to have that the second derivative is 0. Okay, because you're going from negative second derivative to positive second derivative. So at the point where you make the transition, you have 0 second derivative. All right. Any questions about this?
Hello, Bryce?
Yeah, James?
Yes. When you found the second derivative of the cubic function s cubed, we have it to be 6x. And you
Mm-hmm.
say when S equals 0, it determines an inflation point where it will be concave downward and concave upward. And you
Yep.
see when it's a negative, from negative to positive is, let's say, concave, and a concave downward, right?
Yep.
And from positive to negative is concave upward.
Well, it's concave upward to concave downward if it's going
Yeah.
positive or negative.
So if you import the value of S equals 0 to the second derivative, which is 6 times 0, if it is less than 0, it will be
No,
negative numbers.
it's equal to 0, right?
It's equal to 0.
Right. So at the
Well,
inflection point, it's neither concave up nor concave down. So at the point where it's actually equal to 0, it's neither one. It's the transition point between the two of them.
that's inflation, right?
That's the inflection point. Yeah. So you can think of an inflection point as a point where the graph is neither concave up or concave down.
So if you pick any point from lambda greater than 0, like positive lambda, you will always be going concave upward. And
Exactly.
likewise, if you pick any lambda from lambda less than 0, you all becoming concave downward.
Exactly. So I'll label it this way. It's concave down with f double prime of x less than 0. The green is concave up with f double prime of x greater than 0. And the inflection point is just the inflection point. This is going to be f double prime of x is equal to 0. But I want to just say it's not just that f double prime of x is equal to 0, but it's also that it goes from concave down to concave up. You can imagine some graph where f double prime of x equals 0, but it's concave up on both sides of that. Like that could happen. It doesn't happen in this example, but there are other examples where it could happen. And if that happens, then it's not an inflection point. So an inflection point doesn't just mean f double prime of x equals 0. It means that the graph actually changes its concavity there. It means it actually changes from concave down to concave up or from concave up to concave down. So you need f double prime of x to be equal to 0, but you also need there to be this change that happens. All right, other questions?
Yeah, yes, sir.
Yes, Prince.
Yeah, I want to know as to whether this is a rule or a theory that is proving
This is a
that
definition.
it concave, yeah, as to whether concave downward of double prime of x is always going to say it is a theory of
Oh, yes.
or
So this is something that we proved 2 weeks ago, that when f
okay,
double prime is positive, or maybe even 3 weeks ago, when f double prime is positive, it's concave up, and when f double prime is negative, it's concave down. That's something that we did, I think maybe 2 sessions ago.
okay, thank you.
Yeah, you're welcome.
Hello, boys. Hello.
Yes, James?
Yeah, based on that, let's say inflation point.
Mm-hmm.
So because we found a second derivative, we just have 6x and
Mm-hmm.
s equals 0 will lead all to be 0. Why if
Mm-hmm.
we to find a second derivative of another function where we have a constant? That's how we find the second derivative, but we still have a constant and s equals 0.
Mm-hmm.
Will there be a point of inflation?
No, right. So x equals 0, there's no reason for x equals 0 to be a point of inflection, right? That only happens if the second derivative there is 0. So if f double prime of x is some constant, then if it's a positive constant, the graph will just always be concave up. And if it's a negative constant, then the graph will always be concave down. The second derivative exists here. It's equal to 0.
Yeah,
Yeah.
I'm saying it because if you put x, the value of x to be 0, you have the whole function equals 0, second derivative equals 0. 6 times 0 is equal to 0.
Right. I mean, that's this example. But there can be, I mean, okay, so if the second derivative is just always 0, then in fact your function's just going to be a straight line, and a straight line doesn't have concavity, right? So a straight line is neither concave up nor concave down. If you have a linear function, the second derivative will always be 0, and that means it's never concave up or concave down. It's just a straight line. But for anything else, where you have the inflection point, it doesn't matter. I mean, this function, it's just a coincidence that it's at x equals 0. There's no significance to x being equaling 0. The only significance is that f double prime at your point is 0. And that's what's going to alert you that there might be an inflection point.
Negative numbers.
Okay, you're welcome. Other questions? Okay, so what is the second derivative test? It's another way of trying to determine whether you have a local minimum or a local maximum somewhere. So it says if f is a twice differentiable function, that just means it has a second derivative. You can take it. And if f prime of c is equal to 0, so that means here you have a critical point or a critical number. Remember, the local minimum or local maximum, they happen at critical points. So we want to know which one it is. Well, the second derivative test is nice and simple. It says that if f double prime is greater than 0, you have a local minimum. And if f double prime is less than 0, you have a local maximum. And again, this is pretty easy to see graphically, right? So if I've got a critical point where f double prime of c is greater than 0 means concave up, right? So if this is my C here, and I have a critical point where the tangent line is horizontal, that's what the critical point means. F prime is 0, and F double prime is positive because this is concave up, then we can see from the graph that this thing here is a local minimum. And similarly, if I've got my graph over here, if this is my point C, and again, I have my critical point where the derivative is 0, got a horizontal tangent line. And here we have f double prime of c is less than 0, meaning this is concave down. When it's concave down, it's going to tell you here that this is your local maximum. Okay, so that's all this. So the second derivative test is actually simpler than the first derivative test. You have a critical point and you just want to check whether it's a local minimum or maximum. Well, if the second derivative is greater than 0, it's going to be a minimum because that's what happens when you're concave up. And if the second derivative is less than 0, it's going to be a local maximum because that's what happens when you're concave down. And the warning that I want to give here, warning, is that if f double prime of c is equal to 0, then you can't make any conclusion. So then no conclusion. Excuse me. So yeah, the second derivative test just fails. If f double prime of c is equal to 0, no conclusion, and instead you have to use first derivative test. Okay. Okay, so you just can't use this if it's 0, then usually it will be an inflection point, but what you actually have to do is just draw it or take the first derivative and see if it goes from positive to negative or if it goes from negative to positive or if it just stays positive or stays negative, in which case you won't have any kind of local extremum at all. Okay, so the second derivative test is a pretty easy way to check whether something's a local minimum or a local maximum. Okay, so we're going to do this all with like an actual example, and we'll show how we can use this to help graph functions. Okay, but before we do that, any questions about the second derivative test here? Okay, great. Oh, James, now I see your question. Okay, yeah. This is the answer. Okay, so let's do an example. So let's say, oops, sorry. Let's say that f of x is 4x cubed plus 3x squared minus 6x plus 1. We want to find all of the local minima and maxima and classify them, meaning, what are they? Which are the local minimum and the local maxima? Where is the function increasing, decreasing, concave up, concave down, and does it have any inflection points? So the way that you approach this is you first compute f prime of x and f double prime of x. Right, so here we have the power rule, right? F prime of x is equal to, well, 4x cubed becomes 12x squared. 3x squared becomes 6x. And then minus 6x becomes minus 6, right? And then the plus 1 becomes 0. And now f double prime of x, we take another derivative. So the 12x squared, we bring the 2 down.
24
24, exactly 24x. And then the 6x
plus 6.
becomes just 6. Great. So this is what we compute first. So the way that you do these types of problems, second, what you do is you solve f prime of x equals 0 and f double prime of x equals 0. You want to solve where all of these are equal to 0. So for the first one, we have f prime of x is equal to 12x squared plus 6x minus 6. If you want to set that equal to 0, you can divide everything by 6. So you have 2x squared plus x minus 1 is equal to 0. And then I guess we're just going to use the quadratic formula for this. We'll get that x here is equal to minus 1 plus or minus the square root of, so b squared minus 4ac. So that's 1 here. So you're going to get 1 and then plus 8. So, 1 minus negative 8 divided by 2. And this is equal to minus 1 plus or minus, well, it's the square root of 9, right? So square root of 9 over 2. And so this is going to be equal to 1 or minus 2, right? Yeah. See, we could have factored this, but I just used quadratic formula instead. So the zeros for f prime of x are 1 or minus 2, and f double prime of x is a little bit easier. You just have 24x plus 6 equals 0, and that's the same thing as 24x equals minus 6, and that's the same thing as x equals minus 6 over 24, which simplifies to minus 1/4. Okay, so I just want to remember all of these numbers, 1, minus 2, and minus 1/4.
Yeah, a question,
Yes,
sir.
Prince, yes.
Yeah, suppose the f prime of x, which I have 12x squared plus 6x minus 6 equal to 0. Suppose I just do it that way and then use a quadratic equation formula without dividing as you did the simplest form. Will you say get the same answer?
Yeah, and I also realized that I did this wrong. Sorry, I forgot to divide by
You
I
did
have to
reduction.
divide by 4, not by 2. Sorry, I used the quadratic formula wrong. So it's not actually 1 and minus 2. This is actually going to be apologies, 1/2 or minus 1 when you do this, because you're going to get either 2 over 4 or minus 4 over 4. I forgot the 2a in the denominator.
Okay.
Sorry, yeah. This is what
So
we.
so now back to my question now, so we can
Yep.
clarify everything now.
Mm-hmm.
Yeah, okay. So we are already using the quadratic equation formula, but let's take for instance the problem with me comes in with 12x squared plus 6x and minus 6. If for any reason we want to leave it like they without breaking it down, will the answer still remain 1 or 2 and this negative 1?
Yeah, I mean, solving this equal to 0 in any method will always give you the same answer. Yeah, so if you want to factor it, you'll end up getting the same answer.
Okay, it's understood.
Has
So
to be
this
the
is
same.
answer.
Yeah.
Yeah.
Okay. Okay. So we've done 2 steps. We computed these derivatives and we solve for when they're equal to 0. So what we really want to understand, what's this question asking? We're trying to understand, when is the function increasing and decreasing and concave up and concave down? What we really want to understand is when is the first derivative positive or negative, and when is the second derivative positive or negative. So what we're going to do for the third step is that we're going to draw a number line. Okay, so I'm just gonna recap what this is. So f prime of x was equal to 12x squared plus 6x minus 6. F double prime of x was equal to 24x plus 6. And we had that this was equal to 0 at x equals 1/2 and minus 1. And this here was equal to 0 at x equals minus 1/4. Okay, I'm just copying what we had from last time. So the third step here is that what I like to do is I draw a number line and label all of the points where f prime of x equals 0 or f double prime of x is equal to 0. Okay, so I'm going to draw a number line here, and I'm going to label the point minus 1/4, and I'm going to label the point minus 1 over here, and I'm also going to label the point 1/2 over here. Right? Okay, so here's how I do this, right? Okay. So this would be plus 6, right? Yeah. Okay. Okay. So now what do I do? For the top of the number line, I'm going to try to understand where this is increasing or decreasing. So I look at where that first derivative is equal to 0. So that's here at minus 1 and here at 1/2, right? And so what I'm going to do is I'm going to punch in a point in each interval to check whether the first derivative is positive or negative. So here I'm going to have the f prime of x is going to be above the number line, and the f double prime of x is going to be below the number line. So over here, I'm going to plug in a point. Let's say x equals 0. That's an easy point. I'm going to plug that point um, into the first derivative. So 12x squared plus 6x plus 6, if I plug in x equals 0, I get minus 6. So that tells me that f prime of x is going to be negative at a point in this interval, which means it's going to be negative in the whole interval because we know it's not crossing 0 in this interval. So here I'm going to write negative. And really what's going on is I plugged in one point. You can pick any point that you want. In this point, I just chose 0 because that's the easiest thing to plug in. So in this interval, f prime of 0 is equal to minus 6. So that means it's going to be negative in the whole interval between minus 1 and 1/2. So likewise, over here, I can try to plug in something greater than 1/2. Let me just plug in f prime of x, f prime of 1. That's probably the easiest point to do. F prime of 1 is going to be 12 plus 6 minus 6. So that's equal to 12, which means that the derivative is positive in this interval. I'll put this in parentheses. And then over here, I have to try the third interval, right? These zeros split up the number line into 3 parts. So I've got to do this part. I'll plug in a point over here, maybe minus 2. And f prime of minus 2 is what? We get 12 times minus 2 squared. That's 12 times 4, so that's 48. Plus 6 times minus 2 is minus 12, so 48 minus 12 is 36. And minus another 6 is 30. So we get f prime of minus 2 is 30, which means this is also positive over here. And maybe let me, if I change this, does that make it easier? It might maybe make the screen a little bigger. Okay. Okay, so this is what I want to do is I'm trying to figure out where is the first derivative positive and where is it negative. Okay, so I break it up into the places, I break it up at points where the first derivative is equal to 0, and then I just pick a point in each interval and plug it in, and that's going to tell me about the behavior on the entire range. So that's going to tell me here it's positive, here it's negative, and here it's positive. Okay. So I can do the same thing for the second derivative. I see where's the second derivative equal to 0? Well, that's at minus 1/4 over here. So I'll break up my number line here at minus 1/4. And now I want to see, all right, so is the second derivative positive or negative? Well, if I plug in a point that's bigger than minus 1/4, right, I now don't care about minus 1 or 1/2. I only care about where the second derivative is equal to 0. So that's splitting up my number line into 2 pieces here. So if I plug in something greater than 1/4, let's say I plug in 0 to the second derivative. When I plug in 0 to the second derivative here, I get 0 plus 6, that's 6. So here I'm going to get that this is positive. And that's because f double prime of 0, for instance, is equal to 6. And now over here to the left of 1/4, I'm going to plug in something that's below 1/4. So maybe minus 1. That's the easiest thing to do. If I plug in minus 1 here, I get 24 times minus 1, minus 24, plus 6 is minus 18. So that's going to be negative. So I get here that f double prime of x is negative. Okay. I've got kind of a line between these two. And a way of seeing that, right, is f double prime of minus 1 is equal to minus 18. Okay, so now we've done all the setup and we're ready to start answering the questions. We basically know exactly where f prime is positive and where it's negative. And we also know exactly where f double prime is negative and where it's positive. Okay, so just to recall, we started by computing f prime and f double prime. Then we solved exactly for where they were equal to 0. And then we saw that these points where it's equal to 0, those points chop up the number line into pieces. And for each piece, we can determine whether f prime is positive or negative by plugging in a point. And we can also determine whether f double prime is positive or negative by plugging in a point in each part. So now it's asking, what are the local minima and maxima, and classify them. I spelled that wrong. And classify them. So, well, the local minima and maxima, we have to look at the critical points. So local minima and maxima, well, we know that they only happen at the critical points. So the critical numbers are exactly where the first derivative is 0. So we have that here. It's 1/2 and minus 1. These are the critical numbers. And so if we want to know, does this have a maximum or a minimum at those numbers, probably the easiest thing to use is this second derivative test, right? We can just look at the second derivative and see if it's a local minimum or a local maximum. Remember, positive means minimum and negative means maximum. Okay, so let's start. Okay, if we look at minus 1 over here, that's a critical point, critical number. What about the second derivative? Well, the second derivative there is negative. So that means x equals minus 1 is a local maximum. Right? That's because f double prime of minus 1 is negative. And also x equals 1/2. Well, let's see. X equals 1/2. What do we know about the second derivative? It's positive. And so that means it's a local minimum. F double prime of 1/2 is positive. Okay. So maybe I could say, a fourth step is use derivative tests. Okay. All right, so this told us whether we had a local maximum or minimum at these critical points. And then the last thing is, where is the function increasing, decreasing, concave up, concave down, and does it have any inflection points? Well, this we can read off directly from the number line, right? So f of x, it's increasing on exactly the interval where the first derivative is positive. So when it's less than minus 1 or greater than 1/2. So it's increasing on, the interval minus infinity to minus 1 and 1/2 to infinity, right? This is what we just read off the number line, exactly where the first derivative is positive. It's decreasing exactly where the first derivative is negative. That's between minus 1 and 1/2. So it's decreasing from minus 1 to 1/2. It's concave up on, well, concave up just means the second derivative is positive. So that happens everywhere where you're bigger than minus 1/4, right? So it's on minus 1/4 to infinity. And it's concave down exactly where the second derivative is negative, which is everything that's less than 1/4. So it's concave down on, this is Yes, it's concave down on negative infinity to negative 1/4. Okay. And the last question is, are there any inflection points? Well, what's an inflection point? An inflection point is where the second derivative changes either from negative to positive or from positive to negative. So we see from looking at this that there's exactly one inflection point. Right at x equals 1/4, this function goes from negative to positive. Right? So I'll just write this last part down over here. There's an inflection point at x equals 1/4. Okay. Okay, so that answers everything in the question. So this kind of question, it takes a little while to do, but really all that's happening is you're finding out everywhere where the first and second derivatives are 0. You write down all those points on the number line, and then you have to do for the first derivative, where is it positive and negative? For the second derivative, where is it positive and negative? And then you can read off all of the information from this labeled number line. So yeah, I apologize, this screen maybe has a lot written on it. But all of these final answers that you want is, what happens about the local minima and maxima. You can read this all off from understanding the derivatives. How do you know when the function is increasing or decreasing or concave up or concave down? Again, you can just read that all off from the derivatives. So all of the information that you need is on this number line. And to get this number line, you have to find where the first and second derivatives are equal to 0, and then test a point from each part of the line to see whether it's positive or negative in that part. Okay? Sorry, x equals negative 1/4 here. Okay. Okay, so any questions on this?
Obers?
Yes, James?
Yeah, relating to the local maximum and the local minimum at
Mm-hmm.
point at the point -1,
Mm-hmm.
I'm saying like I want to get something clear. The graph starts going up when it reach a -1. You see, I have to count down. It starts
Exactly.
coming down. So at that point, it's the local maximum.
Mm-hmm. Yeah,
So
goes
now
from up
it
to
came
down.
down, and when you see that it about to go up at 1 or 2, it started to go up. I mean, it do a valley to go up at the positive value. So that's the local minimum.
Exactly. So what you're doing is the first derivative test reasoning, which is completely valid. I use the second derivative test here, but you can use either one. So you use the first derivative test, which says it goes from increasing down to decreasing, so it's a local maximum. I use the second derivative test, which said the second derivative is negative, which means it's a local maximum. They're both valid. You can use either one.
Yeah, like I used to the first derivative test. So like the second derivative, can you maybe explain it more clearer so I can understand it? Because normally
Right.
I don't see that you have to draw the graph to understand which one is local and which one is
Yeah,
let's say.
so eventually we'll draw this whole graph, but the point of the second derivative test is you've got your critical point and you know the second derivative is negative. So what can the graph really look like when the second derivative is negative? Well, it can't look like this. That would be a positive second derivative. So it has to look like this. It has to look like it's spilling water. That's your second derivative test. And so when a graph looks concave down like this, wherever it has its critical point, wherever it ends up having this horizontal tangent, that's going to have to be the maximum because this is what a second derivative negative graph looks like. I mean, second derivative positive graph looks like this. A negative graph looks like this. Okay, so that's the reasoning of the second derivative test. But of course, you could also just reason the first derivative test. In this graph, the first derivative goes from being positive to being negative. So maybe it's worth it to just graph this so that we can see what it looks like. So for now, I'm just going to do a graph on Desmos. So let me share my screen here so that you can see a graph on Desmos. So the function here was 4x cubed 4x cubed plus 3x squared plus 6x minus 6. Sorry, minus 6x plus 1. Minus 6x plus 1. Okay, so if we see what's going on, and maybe I'll zoom in a little bit over here. So let me just zoom in a little bit here. So what did we see? Well, we saw that, I mean, I can't show you the notes right now, but we saw that at -1, there was a local maximum. That's exactly what we see here. In fact, if you plug in -1, you're going to get 6 to the original function. So the function goes up and then down, and then at +1/2 was the local minimum. That's right over here. It's the point +1/2 and then -3/4 when you plug it in. And so the function was increasing and then decreasing and then increasing again. And what happens with the concavity? Well, we saw that there was an inflection point at about -1/4. Okay, so that's about right here. This is -1/4. If you look at it on the graph, it's over here. And what you see is, oh yeah, so this is exactly -1/4 here. And so what you see on the graph is before this point, the graph is concave down. That comes from the second derivative. And then at this point, at -1/2, where are we? -1/2 here, then the graph switches from concave down to concave up. So it becomes concave up for the rest of the time over here. Okay, and exactly at this point, at the -1/4, where are we? At -1/4 over here. Yeah, this is exactly the point where the graph switches from being concave down to being concave up. So this is the inflection point on the graph. Okay. So you can see kind of graphically what's going on with our computations. It's telling you exactly when is the graph increasing, when's it decreasing, and when's it increasing again. And it also tells you the precise moment where the concavity changes. Okay, so it's good to see the graph from this. We'll do an example where we actually draw the graph without using a calculator, just by using the information that we have from looking at one of these examples. Okay. Okay, so just wanted to show the graph. Does anybody have any questions while I show the graph, or should I go back to my notes? Okay, let me go back to my notes. Share here. Oh, here we are. Okay, good. Okay, great. Okay, so now we can actually do the homework exercise, right? So now we can actually do this this homework exercise which is a similar type of question. So for this function, f of x equals 2 plus 2x squared minus x to the fourth, we want to find all of the critical points and the inflection points, and we're going to classify the critical points into local maxima, local minima, and neither. And on what intervals is the function increasing, decreasing, concave down, concave up? And I'm going to add another part of the question, which is sketch the graph of this function. Right? And this is a graph that you probably don't know how to sketch just from looking at it, because it's a fourth degree polynomial. We don't really learn how to just draw the graph of a fourth degree polynomial. But I claim that from what we've done, we should be able to do that. Okay, we'll be able to do the sketch. So first, we need to find all the critical points and the inflection points. So we need to still do our same first step that we had before. Right, so first step, let's calculate the first and second derivatives. So f prime of x, well, the 2 disappears, and so we end up with 4x, just 4x minus derivative of x to the fourth is 4x cubed. And then the second derivative is the derivative of 4x is going to be 4, and the derivative of 4x cubed comes to 12x squared.
Yes, sir.
Yes, Prince.
Yeah, I have a concern with the power.
Mm-hmm.
Yeah, so because we have a 2x squared and minus 4s, 4, I got the s raised to the fourth power. So
Right.
do the power don't affect any solving problem because we can move from square to go straight to the fourth power. So what becomes of third power? Can it
It's
be
just
indicated? So
it's
just
just
for in
not
case.
there. I mean, if you want to, you could write plus 0x cubed if you wanted to, but you don't have to. There's no reason to do that, right? There just is no third power term here. And remember, when we do derivatives, derivatives of things that are added and subtracted, you can just do them piece by piece. So if I want the derivative of this, I just take the derivative of 2, and I take the derivative of 2x squared and I add it, and I take the derivative of x to the fourth and I subtract it. It doesn't matter if there are any terms that are skipped. I just do each term as it appears.
Okay, thank you so much, sir.
It doesn't matter that there's a skip. Okay. So second step, we're trying to set these equal to 0, right? So this is pretty easy, right? 4x minus 4x cubed equals 0. In general, a cubic equation is hard, but in this case, it's pretty easy because you can pull out a power of 4x. So you get 4x times 1 minus x squared is equal to 0. And this factors into 4x, 1 minus x, 1 plus x equals 0. And this is going to give us either x equals 0, x equals 1, or x equals minus 1. Okay, so we've got three different things here, three different answers here in the second step. This is going to be where f prime of x equals 0. And then what about f double prime of x equals 0? We're going to have 4 minus 12x squared equals 0. And that's the same thing as 4 equals 12x squared, which is the same thing as 1 equals 3x squared, which is the same thing as 1/3 equals x squared, which is the same thing as 1 over square root of 3 equals x, or plus or minus 1 over square root of 3 equals x. And again, you can rationalize the denominator if you want, but you don't really need to. Okay? So these are going to be the critical points, right? So the critical points, we have here the critical points are x equals 0, x equals 1, and x equals minus 1. That's where the derivative is equal to 0. The inflection points are probably going to be these points right here, x equals 1/3, 1 over root 3, and x equals minus 1 over root 3. But technically, we don't know that yet. In order to know that these are inflection points, we have to actually see that the second derivative goes from positive to negative. So we're not going to be able to do that until we do our second step, or sorry, our third step with the number line. So we're going to need to do a number line step in order to actually figure out where these inflection points are going to be. The critical points are fine. Critical points just means it's just wherever that derivative is equal to 0. Yes, Rosh, you have a question?
Yeah. Hello?
Mm-hmm. Yep.
Yeah. Yeah. I want to ask if, for example, maybe you have a problem solving, right? Then you do the first derivative, which is that the critical point, or then the second derivative is that the inflection point?
Yeah, exactly. Yeah, so it's all part of the second step. We're just figuring out everywhere where the first derivative is 0 and everywhere where the second derivative is 0.
Okay.
Yeah, a
Yeah.
question.
Prince, yes.
Yeah, Prince. Yes, sir. Is it possible to have a first prime, second prime, and third prime in derivative as such prime arises that is?
Yeah, you can do as many derivatives as you want. So we could take a third derivative, and that would be 0 minus 24x. So it'd be negative 24x.
Yeah, that's
And you
right.
can take a fourth derivative, that's going to be minus 24. And you could take a fifth derivative, which would be 0. But
Okay.
the geometric meaning of the third and higher derivatives is not so clear. So it's what we're doing here is we're trying to be able to understand what graphs look like and how that's related to derivatives. And when you get past the second derivative, it's not so clear what everything means for the graph.
Okay, thank you.
Right?
Understand.
So that's why we only do the first two. But you can do as many as you want. You just don't have to.
Okay.
Okay, good. Yeah. Other questions?
Hello?
Yeah, Saley?
Yeah.
Mm-hmm.
Yeah, well, if I want to rationalize the denominator and get rid of the plus and negatives or sign there, the
Sure. I
plus
mean,
or negative.
well, the plus or minus is still going to be there, but you can rationalize if you want to. Yeah, you can multiply by root 3 over 3 if you want to. So that would also give you x equals minus plus or minus if you multiply by radical 3 in the numerator and radical 3 in the denominator, you're going to get 3. What's usually more important is to actually get this to be some kind of decimal. So this is roughly 0.587, I think, if I recall correctly, or 588 maybe. 588. What is root 3 over 3? 577, sorry. 577. So it's going to be more important for our purposes when we're doing number lines is to have some idea of what this thing is as a decimal, so we know where to put it. So rationalized, non-rationalized is not so important, but it will be important to know that this is about 0.57 or minus 0.57.
Okay.
Yeah. Okay, other questions? Okay, so now we have to do our number line. Okay, so again, this is going to take a little while, but it's worth doing. So we're going to have to do the number line now. So let me do it like this. And I'm going to just recall. So f prime of x was equal to 4x minus 4x cubed. F double prime of x was equal to 4 minus 12x, 12x squared. And this was equal to 0 at x equals 0 minus 1 and 1. And this was equal to 0 at x equals plus or minus 1 over square root of 3, which was the same thing as plus or minus 0.577, roughly 0.577. Okay, so now we do our number line. Okay, so I'll draw the number line over here. And we label every point that is one of these zeros. So I'm going to label the 0 here, the 1 over here, the minus 1 over here, and then over here is minus 1 over root 3, and then over here is plus 1 over root 3. Well, I won't write the plus. I'll just write 1 over root 3. And again, we have f prime of x on the top of the number line and f double prime of x on the bottom of the number line. And so first, for the first derivative, I'm going to circle all of the points where where the first derivative is equal to 0. And what I have to do is find a point to plug in each of these parts where I can check whether the first derivative is positive or negative. So over this part, maybe I'll plug in 2. That's the easiest. So 4 times 2 is 8, minus 4 times 2 cubed is minus 32. So I have 8 minus 32 is negative 24. So here it's going to be negative. That's because f double prime of 2 is equal to minus 24. Now here is a little harder because I don't have a whole number that I can plug in, so I have to plug in something like 1/2, which is maybe as good as I can do. So if I plug in 1/2 over here, I'm going to get 4 times a half is 2 minus 4 times an eighth is a half. So that's 2 minus a half, which is 3/2. So that's actually going to be positive. And here I have f prime, oh, sorry, that's f single prime. F prime of 1/2 equals 3/2, turns out to be. Over here, I also have to plug in something in the middle, so why not I try minus 1/2? That's the easiest. Minus 1/2, I'm going to get negative 2 minus 4 times minus 1/2 cubed, so it's negative 2 minus negative 1/2. You can check it on your own time if you want, but it turns out this is going to be negative because f prime of negative 1/2 is going to be negative 3/2. And then lastly, I plug in something that's less than minus 1. So let me just try minus 2. And it turns out that f prime of minus 2, if I plug that in, I'm going to get negative 8 minus negative 32. That's going to be equal to 24. And so I get positive. Okay. So this is what I get for the first derivative. Now for the second derivative, I do the same thing, but I punch my interval at points where the second derivative is 0. So I first go and plug in something that's bigger than 1/3. The easiest thing is probably 1. So I plug in 1 to the second derivative. That's 4 minus 12 times 1 squared. That's 4 minus 12. So in this case, the second derivative here is going to be negative. That's because f double prime of 1 is equal to minus 8. Here I can plug in something between minus 1/3 and 1/3, so I may as well do 0. That's as easy as it gets. So f double prime of 0 is just 4, right? So here it's going to be positive because f double prime of 0 is equal to 4. And then lastly, I'll plug in minus 1 over here, something that's less than minus 1 over root 3. If I plug in minus 1, I get 4 minus 12 times minus 1 squared. And that's 4 minus 12. That's still minus 8. So here I'm going to have negative. And that's because f double prime of minus 1 is also going to be minus 8. Right? So if I want to, I can draw kind of little lines here, dividing up my interval. So now we can write down the inflection points. What are the inflection points over here? Well, they're going to be exactly where you change from negative to positive, where the second derivative changes from negative to positive, or when it changes from positive to negative. So we see that every point where the second derivative is equal to 0 actually does give us a change. We go from negative to positive to negative. So the inflection points will be exactly at x equals minus 1 over root 3 and x equals 1 over root 3. Okay, this is going, this is because, sine of f double prime changes at these points. So those are the inflection points. Remember that we already have the critical points. We already said the critical points were at x equals 0, 1, and minus 1. Now we need to classify these points. Maybe we'll use the first derivative test, the way James was doing it. So we want to classify these critical points. So minus 1, 0, and 1. So the critical points, or the critical numbers, well, we have at x equals minus 1, we have that the first derivative goes from positive to negative. So you go from increasing and then decreasing. That means it's got to be a local maximum because you're going from increasing and then decreasing. So x equals 1 is going to be a local maximum. Sorry, x equals minus 1 is a local maximum. X equals 0, the next critical point. Well, the first derivative goes from negative to positive. So the function goes from decreasing to increasing. That means it's going to be a local minimum. Okay, and then the last critical point, we have x equals 1. Here, the first derivative goes from positive to negative. So you go from increasing to decreasing. Okay, so that's going to be a local maximum. Okay. And now, sorry, I just wanted to check one thing else. Okay. Yeah, okay. Okay. So that's how we do this. Okay. And so now we want to know on what intervals is the function increasing, decreasing, concave up, and concave down. Maybe I'll just say, so function, this we can also just read off from the number line, is increasing on, well, that's exactly where the first derivative is positive. So when you're less than minus 1 and also when you're between 0 and 1. So it's increasing on minus infinity to minus 1 and 0 to 1. It's decreasing everywhere else. So when you're negative, when the first derivative is negative, so that's between -1 and 0 and between 1 and infinity. So -1 to 0 and 1 to infinity. It's concave up wherever the second derivative is positive. So that's between -1 over root 3 and 1 over root 3. So -1 over root 3 to 1 over root 3. And it's concave down wherever the second derivative is negative. So that's when you're less than -1 over root 3 and greater than 1 over root 3. So it's concave down on minus infinity to 1 over root 3. So to -1 over root 3, and then also from 1 over root 3 to infinity. Say and here. Okay. Okay. Good. All right. So this is what we have. So this is the function. So we have all of this information about the function. And what we're going to want to do is now graph. We're going to want to figure out how we can use this information to graph the function. Okay? And what we're going to do basically is we're going to look at all of these important points. We're going to be able to graph all of these points, and then we're going to be able to connect the graph up between these points using this information that we have about, whether the graph is positive or negative, whether the first derivative is positive or negative, and whether the second derivative is positive or negative. So I would love to see, no, that's not what I want. No, I don't want to use the lasso. Okay, got it. I just want to see what happens if I do this? Okay. So I'm gonna try something else here. So let me see what happens. Can I copy this over here? So like how to graph. Okay, so what happens if I try to paste? How do I paste? I need to learn how to use this app better. Oh, where's this lasso tool? I had this lasso tool. What happened there? No. Huh. Well, I can't figure this out. So let me. Oh, right. Okay, what if I do this? Huh. Okay, well, I can't figure this out. Okay, so I'm going to just try to copy this down. Okay, I'm going to copy this down. Again, this number line. Okay, so I'm going to copy this down. Here was -1 over root 3. Here's -1, -1 over, yeah, sorry. I'm just going to copy down a simplified version of this. So we have -1, -1 over root 3, 0, 1 over root 3, and 1. And then I have f prime of x and f double prime of x. And I'm just going to copy in positive, negative, positive. So I'm going to just say here we had positive, and then here we have negative, and here we have positive, and here we have negative. And then over here we had negative, and then positive, and then negative. So this is kind of a shorthand copying of what we had before. So now to graph this, I'm going to draw some axes. I'm going to label these important points. So I have 0, I have maybe 1 over root 3, and I have 1. And then here I have -1 over root 3, and here I have -1. And now I'm going to plug all of these points into the original function in order to get some values. So for the original function, what do I have? I have f of 0. Remember, f of x here was equal to 2 minus 2x squared plus x to the fourth, right? And that was the original function? Yes. Sorry, 2 plus 2x squared minus x to the fourth. Okay. So what happens? Well, when I plug in 0, f of 0 is just going to be 2. F of 1 is 2 plus 2 minus 1. So f of 1 is equal to 3. F of minus 1 is equal to, we have 2 plus 2 minus 1. F of minus 1 is also equal to 3. F of 1 over root 3 is, well, I have 2 plus 2 times a third, right? 1 over root 3 squared is a third. So 2 plus 2 thirds, that's 8 thirds. And minus x to the fourth is 1/9. So it's going to be, turns out this is going to be 8 thirds minus 1/9, which if you simplify it, this comes out to be 23 ninths. And then it turns out that f of minus 1 over root 3 turns out to be the same thing. It's also 23 ninths. Okay, so let me label these points, right? So I'll label, let me draw my axis over here. So I have 0, comma 2 is a point on the graph. I have 1, comma 3 is a point on the graph, and so is minus 1, comma 3. And then I have at 1 over root 3, I have 23 ninths. That's kind of between 2 and 3. That's kind of over here. And at 1 over root 3 and minus 1 over root 3, I have 23 ninths for both of those. So these are 5 points on the graph. Okay. So these are 5 points on the graph. And so let's just try to draw all the segments. So what happens over here? When we're to the left of minus 1, the function is increasing, but it's also concave down, right? So f prime is positive, but f double prime is negative. So it's increasing concave down. So what that looks like is something like this. Increasing, but concave down until you get to this point. Then what happens here between minus 1 and minus 1/3? It becomes decreasing, but it's still concave down. So decreasing concave down kind of looks like this. It goes down, decreasing, but it's still concave down. It's like a mountaintop. Now what happens between minus 1 over root 3 and 0? It's still decreasing, but it now becomes concave up, right? The second derivative is positive. So that means we've got our inflection point. It's going to still be decreasing, but it's now going to look kind of concave up. It's going to look like a valley instead of a mountaintop. What's my next interval? Between 0 and 1 over root 3. It's now increasing and concave up. So to draw that, ends up looking like this, increasing and concave up. Goes from here up to here. And now between 1 over root 3 and 1, it's increasing because the derivative's positive, but also concave down. So that looks more like going up to a mountaintop, increasing but concave down. And then lastly, what happens between 1 and infinity? It's now decreasing and concave down. So decreasing and concave down looks like this. Okay, so this is our sketch of the graph of this fourth degree polynomial done completely by hand, right? We had to do some calculus to compute things, but basically we did this completely by hand. We didn't use any calculators, okay? And all of this is just based on what the graph looks like, knowing when is the first derivative positive or negative and when is the second derivative positive or negative, right? So if we go back, there were a lot of steps here. It's a long problem. We had to calculate the first derivative and the second derivative. We had to solve for when they're equal to 0, find all the critical points. Then we had to divide up the number line based on the critical points and also based on the inflection points, where the second derivative is 0, figure out where is the first derivative positive and where is the second derivative positive. But once you have all of this information, which is getting distilled into this shorthand graph over here for positive and negative, you can draw each segment of the graph basically just by knowing whether it's increasing or decreasing and whether the graph is concave up or concave down. And so as the test, let's see if this graph that we drew by hand is actually correct. So now I'm going to graph it on the graphing calculator and let's see what happens. So if I graph it on the graphing calculator, so if I go to Desmos And now I'm going to draw this function, y equals 2 plus 2x squared minus x to the fourth. And look, we have exactly what was drawn, what our graph was. Remember, we came up and then over and down like this, and then back up and then back down like this, with inflection points right here around square root of 3. Wait, what happened here? Did I 2 plus 2x squared minus x to the fourth? Oh, yeah. This is fine. I just wanted to zoom in a little bit. Right. So the maximums are at -1 and 1. The minimum's at 0. And there's inflection points around here, right around -1 over root 3 and +1 over root 3. Okay. So the point is this graph of the function, that the scale on the axes is a little bit different, but more or less it looks exactly like what we drew. Okay, it goes up from 3 down to 2. The only reason ours looks different is that the scale on my x-axis is a little wider than my scale on the y-axis. That's why my graph looks flatter. Okay, but this is exactly the same thing. Let me zoom this. Okay, no, this is fine. Okay. Right. So if I had made my scale so that my y-axis points were as far apart as the x-axis points are, then this would look more like the graph that's drawn on Desmos. Okay. Okay, so it's a long, involved question, but the point is it gives you the power to just do this by hand. You can reason what the graph is going to look like just by using calculus. So any questions here? Okay. There was this homework exercise too that I had about redoing the ladder problem in terms of the angle. It turns out it's not any easier than doing it the way that we did it before. So I don't want to go through this. It would take a very long time and probably will confuse people. So we're going to skip that. So here, so here's another example, which will have something like this on the homework. So in this case, I'm going to go in reverse. I'm going to draw a graph. So let me draw a graph that looks like this. How do I want to do it? Okay, let me just draw. Oh no, that's not what I want to do. Sorry, no. That's not what I want. Okay, let me draw the following graph. Okay, this is a graph of y equals f of x for some function. Okay, I want to make sure. Okay. Yeah. Okay, so if I have this graph of y equals f of x, the question is, where are the inflection points if this is the graph of f of x? And so that there's several questions, but the first one is, if this is the graph of f of x, where are the inflection points of f? And so before we even look at these other questions, this should be pretty easy, right? Because how do we see the inflection points? It's where the function goes from concave up to concave down, or from concave down to concave up. So we can answer this question really just by looking at the graph. It looks like over here, we have an inflection point. We kind of go from concave up to concave down. Over here, we have an inflection point. We go concave up to concave down. Looks like we're going concave down, but somewhere around here, we switch to being concave up. And now we've got concave up, and then somewhere around here, we switch to being concave down again. So the red points are going to be, the inflection points of f of x. Okay, so this is a pretty straightforward question. You just label it on the graph. So now, yeah, so let me say this. If graph is y equals f of x. Okay, so any questions about this first problem? It's really just looking to see where it goes from concave up to concave down. The second problem is where it starts to get a little bit more interesting. Okay, your phone percentage is very low. Okay, you'll be able to see the rest on the recording if you end up coming out. We're going to go for another 15 or 20 minutes. Okay. So now what happens if this is the graph of f prime of x? So let's say this is actually the graph of f prime of x. So it's saying I have some function. I'm not telling you what function it is. I'm not even going to show you its graph. I'm just going to say this thing here is the graph of its derivative. So whatever, there's some function f of x, and the graph of its derivative looks like this. And so we want to know, where are the inflection points of the original function? So let's remember, an inflection point is where the second derivative of f goes from positive to minus, right? Inflection point means that f double prime of x goes from positive to minus or from negative to positive, right? Well, that's the same thing as, well, f double prime is f prime prime. That's saying f prime prime of x goes from positive to negative or negative to positive. And so what do we have here? Well, if this is the graph of f prime, this is the second question. So if this is the graph of f prime, then we want to know, when does f prime prime go from positive to negative or from negative to positive? And the answer is, well, we can look at the graph and we want to know, when does the derivative, the first derivative of this graph, right? F prime prime, but f prime is already the graph. So when does the first derivative of this graph go from positive to negative or from negative to positive? And that happens exactly when the graph itself goes from increasing to decreasing or from decreasing to increasing. So what I'm going to do is I'm going to label those points in purple. So when the graph goes from increasing to decreasing or from decreasing to increasing, so up here and then here and then up here and so on. And so these purple points are going to be the inflection points of f of x if the graph is y equals f prime of x. Yeah. So yeah, this is the x-axis here. Okay. So yeah, so it's a little bit tricky what this first question is asking. It's saying, if this is the graph of f prime of x, where are the inflection points of f of x? Well, we want to know, when does, that's the same thing as saying, when does f double prime of x change from positive to negative or from negative to positive? Well, if the only information we're given is f prime of x, well, f double prime of x changing from positive to negative is the same as f prime prime of x changing from positive to negative. And if this is the graph of f prime, so we're asking, when does its derivative change from positive to negative or from negative to positive? And that happens exactly at all of these purple points. That's when the first derivative of this graph changes from positive to negative or negative to positive. And that's what the question is asking. It's saying, when does the first derivative of f prime change from positive to negative or from negative to positive? Okay. And now the third question, which is actually a little easier than the second, is, now imagine this thing is the graph of f double prime of x. Then we want to know, what are the inflection points? When does if this is the graph of f double prime of x, we're asking, when does f double prime of x change from positive to negative or from negative to positive? Right? It's asking the same question. But in this case, we can just look at it from the graph. We're just asking, when does this graph change from negative to positive, and when does it change from positive to negative? And so I'll use green to color in those points. right? When does it go from negative to positive or positive to negative? Well, it's exactly when it crosses the x-axis. So it certainly crosses the x-axis here, and it crosses the x-axis here, and it hits the x-axis in these two other points, but it doesn't really cross it, right? It doesn't go from positive to negative or from negative to positive here. It just stays positive, and over here it also stays positive. So in fact, the only inflection points are going to be at these green points. So the green is going to be the inflection points if the graph is y equals f double prime of x. Okay, so depending on which function this graph represents, the locations of the inflection points of f are going to be different. If this graph just represents f itself, then the inflection points are just the inflection points on the graph. You just see the points that look like inflection points, the change in concavity. If the graph represents f prime, then the inflection points are actually going to be the critical points of the graph. It's going to be exactly where f prime prime changes from positive to negative or negative to positive. So where this changes increasing to decreasing or decreasing to increasing. And then lastly, if this thing is actually just the graph of f double prime of x, then the inflection points are actually just where that graph changes from negative to positive and from positive to negative. And that happens here at the green points. So we have kind of three different answers. It's the red points for the first question, the purple points for the second question, and the green points for the third question. Okay. All right, so there will be another example like this on the homework that you'll get some chance to practice. Okay, so we are getting to the end. So I don't really want to start the chain rule now because we only have 13 minutes and that's not enough time to start it because I'd rather not have to rush it. So I think I won't do all of this stuff for the rest of the class, which is about the chain rule. We'll do that next week instead. So instead, let me go just straight to the homework. So for the homework this week, we're going to not do parts 3 and 4 because these rely on the chain rule. So these will not be part of the homework this week. So instead, we have these homework exercises 1 and 2, which is just like this exercise that I gave you before. So let's say that we have a graph. Where are the inflection points? Then now suppose the same graph is actually the graph of f prime. Where are the inflection points of f? Where are the critical points of f? Where is f increasing, decreasing, concave up, and concave down? This will be a little tricky question that you may have to think about for a while, but we'll certainly go over it. Of course, I have to actually give you the graph. So let me draw a graph for you. Okay, so I'm going to draw the graph for the homework questions. So graph for homework questions 1 and 2. Let me draw it. So this is going to be a graph. It's from the book. If you want to do this, it's in the book. It's section 3.3, exercise 12, if you want to find it in the book, but I'll also draw it here. Okay, so here we've got 1, 3, 5, 7, 9, and I'm going to mark the other points here, 6, 4, let me mark 4 in the middle there, 2, and 0. And I'm going to have this graph is going to look like this. Oh, no. Up to here, and then down here, and then up to here, and then down like this, and then up. Okay, so this is the graph that we're going to use in those homework questions. Okay. So if we're given by the graph below, what are the inflection points of f? And suppose the same graph is actually the graph of f prime, then what are going to be its inflection points? And then where are, and then a whole bunch of other questions about that if this is the graph of f prime. Okay, so if you want to talk about this on the chat during the week, if you're confused about it, it's meant to be not the easiest problem. It's meant to require a little bit of thought, but we'll go over it in full next week. Okay, and so next time on February 20th, we'll discuss an application of the chain rule called related rates, but actually we're going to first discuss the chain rule and an application of the chain rule called related rates. Okay, and so this is going to be an interesting application. It's kind of saying, as one quantity changes, how do other quantities change at the same time? So this is, very important in all sorts of applications. So we'll start with we'll go over the homework, and then we'll start with some formulas about what's called the chain rule, and then we're going to talk about its application to things called related rates. Okay, so that'll be a little bit more of an applied class than this one today. Okay, so thank you as always for your attention. And I think we'll stop here because it doesn't make sense to start the chain rule. The chain rule, I mean, we'll do it next class, but in the textbook, it's going to be section 2.5 of the textbook. Okay, section 2.5 of the textbook. Okay, and then related rates is going to be section, I think it's 2.7 of the textbook. So 2.7 of textbook. Okay. All right, so let me stop the recording here. Well, actually, let me just give one more minute for you to type your name in. If anybody thinks they forgot to type their name, you can do it now. I think everybody here remembered. I think everybody remembered to type their name. Marcus, did you type your name? I want to just make sure that everybody has typed it. All right, Marcus, I'm not sure if you remembered. So oh, you did. Great. Okay, so I'll stop the recording now.